Okay, so let's try to prove that the limit as x approaches 3 of the expression 4x minus 5 is equal to 7. And let's do this with the epsilon delta definition of a limit. Okay, so I've laid out some stuff to help us get started here. First off, in red we have the epsilon delta definition of a limit, which says, and this should be familiar, the limit as x approaches c of some function f of x is equal to L if and only if we have this right here. For any epsilon greater than 0, we can find a delta greater than 0 such that if the distance between x and c, of course that's just the absolute value of their difference, if the distance between x and c falls between 0 and delta, then the distance between f of x and L, again, that's the absolute value of their difference, that distance must be less than epsilon. Okay? Now that's the general epsilon delta definition of the limit for this particular context. Notice that c is 3, f of x is 4x minus 5, and L is 7. So substituting those things in here, and here, and here, we need to show this in green. For any epsilon strictly greater than 0, we can choose a delta strictly greater than 0, such that if the absolute value of x minus 3 is between 0 and delta, strictly between them, then the absolute value of this expression, 4x minus 5, remember, that's our f of x, minus 7, remember, that's our L, that must be less than epsilon. So this green thing here is what we need to show. Okay, so let's break this green stuff down into its constituent parts. First off, for any epsilon strictly greater than 0, we need to be able to choose a delta. Okay, so for any epsilon greater than 0, choose delta to be something. I'm going to have to figure out what that something is. And there's a restriction on delta. It has to be strictly greater than 0. So whatever I pick here, and I don't know what that's going to be yet, I'm going to have to make an argument that it's strictly greater than 0. Okay? So again, I don't know what this is yet, so I can't make that argument yet, but let me put a little green squiggly line here to remind myself that I'm going to need to write that down. Then we need to show this. We need to show if this happens, then this happens. And at least for this particular limit, we can proceed in a really direct manner to establish this. If this, then, well, something. Maybe we can't get all the way to this statement right away, but maybe we can get to something, and maybe that's going to tell us something else has to be true, and maybe because this is true, maybe that's going to tell us something else is true, and it's not clear how many steps we're going to need here, but ultimately we want to see this guy right here, there he is, as the last line in that implication, in that line of reasoning there. Okay, so we can say with surety, if this, then ultimately that has to be true. If this, then that. Now, finally, we're at a spot where we can take a next step. We see something here that we can go forward with. In particular, looking at what's in between the absolute value symbols here, this is something we could simplify. So let's go ahead and do that. Certainly we can combine the negative 5 and the negative 7 to get the absolute value of 4x minus 12 is less than epsilon. So we're kind of working backwards up the chain. If we know this is true, then certainly we could split that 12 back into the 5 and 7. Can we continue to work our way backwards up this chain of implication? Remember, we ultimately want to get to this statement, a statement involving the absolute value of x minus 3. So one thing we should consider is how can we massage this expression, or this inequality I should say, so that we see an x minus 3 in it. Maybe then we can establish the linkage between these two. Well, looking at this, can't we factor out a 4 here? And notice what that leaves. Precisely the absolute value of x minus 3. That's what we hoped to see. Okay? Now, again, going back to here, notice not only do we have the absolute value of x minus 3, but it's kind of isolated in this string inequality. Over here, we have this extra 4. Okay? Let's try to isolate our absolute value of x minus 3 and see what we get. Okay? Again, trying to work our way backwards. What if I divided both sides by 4? I would get an equivalent statement, right? So that if this were true, then this would be true, right? And then, of course, if this is true, I can distribute the 4 in to the absolute value expression, and I get this. And if this is true, I can split the 12 into the 5 and 7, and finally I get this. Okay? Now, we're so close at this point. Look how similar this is to this statement. What if I picked as my delta epsilon over 4? Okay, so let's go back up here, and let's choose delta to be epsilon over 4. Then, simply rewriting this, we would have this. And if we have this, we certainly have this. All we're doing is ignoring the fact that it's bigger than 0. Okay? So we've connected the two pieces. If this is true, then this is true based on our choice of delta. If this is true, this is true. Okay, because we're just ignoring this inequality involving 0. If this is true, we can multiply both sides by 4 to get this. If this is true, we can distribute the 4 to get this. And if this is true, we can split the 12 into the 5 and 7 to get this, which is precisely what we needed. Okay? There's one last little piece here. Remember, we haven't dealt with this. We need to show that delta is greater than 0 based on how we chose delta. But that's easy, right? I mean, consider the value of epsilon over 4. Epsilon itself was positive, so certainly epsilon over 4 should be positive. So we just write that. Okay, so there's our reasoning right there for why delta needs to be strictly greater than 0, too, based on what we chose it to be. Now, we have shown everything we needed to show over here that we mentioned in green, right here, and so we can conclude the limit as x approaches 3 of 4x minus 5 actually is 7. That's it. That's all there is to it.